Alright, so we're going to get into the second part of your rectilinear motion and dynamics, and we're going to start this second part with velocity. Okay, so the next dynamics, alright, the key idea in the motion, in dynamics is your velocity. So what is velocity? And so if you think about the velocity, I have already explained a little bit about it in chapter 1. It's just the rate of change or position. But remember we did example, right? S versus time, conceptual problem, the previous problem we just did. So velocity is just we're just looking at the rate of change of that position, okay? But this time you're going to look at that position with respect to time, okay? So we're bringing another factor, time factor, in it, means that we are interested in looking at the motion of a particle, let's say, of course, in this example, and not only we're interested in the distance traveled or displacement or total distance traveled, more than the position. We have interest, we want to study, okay, in a time interval. We want to look at its behavior with respect to time. When we say time, it means we want to study this little guy, how it moves from this point to that point, okay? So we're just looking at the activity of that particle in a time interval, and that time interval is measured with two distinct points, okay? So point 1 and 2, and whatever that is happening about that particle motion is what we're looking at. Of course we're talking about the motion, so it's the particle will move, okay? It's going to move from here to here, whatever, and the line itself is a number line coordinate because we're studying, analyzing the behavior of that particle. So the particle is imagined and studied on an axis, okay? So that axis is your coordinate axis, and we name it as a position, So on that line, you know that it has unit, Without the unit number line, we can't be able to identify its initial position or the final position, So we know that this is a coordinate numbered line, and we have a particle that we're studying, and now we are going to study it against time, So with respect to time, we're going to pay attention the change of that particle position with respect to this time interval, okay? And that is velocity, okay? Got it? So the rate, what is the rate that this particle change of position, with respect to time? So the key word is rate, the rate of what? The rate of the change of position with respect to time. It's got to be with respect to time, because without the time, you will never have a rate. Every time we think about the rate, you're thinking of how fast it is. It is going 100 miles per hour, or it's going like 2 miles per hour. So 2 miles per hour. So in 1 hour, if we think about this car can travel only 2 miles, it's slow, In 1 hour, that car can travel about 100 miles, very fast, So that is called the rate, and we call it velocity. So in other words, it tells you how fast, and in which, again, direction, because of this coordinate axis we're studying and analyzing about that motion, there is a direction, So therefore, how fast and in which direction in this example, this particle position is changing. Yeah, it changed from S initial to S final. Yeah, that's the starting point, and that is the ending point. Yeah. Does it take 1 minute to do that, or does it take 0.1 second, or does it take 1 second or 2 seconds? So how fast does it go from here to here? Yeah. So how fast? So there's a time factor in it. So our analysis is not with respect to time. Yeah. Seeing the rate of this guy, the rate of the change of this position, how fast it is. And that's your velocity. So here's the question: if the position isn't changing, if position is here and the next time you look at it and your final position is still right there, no change, even though your time is changing, changing from 1 second, 2 second, 3 second, 4 second, you go and look at it, it's always right here. If the position isn't changing, like the particle is sitting right there, but the time is going. So what is the velocity? Okay, what is the velocity? So what is it going to be? Exactly, the velocity is going to be 0. Why? Because the change in position, we're looking at against the time. So over that amount of time, where is this? So the change in position, change. So I should put a little, time. Your time also is changing. Your time is also changing because it is going from 0 to 1 second, 1 or 2 second, 2 to 3 second. You're looking at the change in position over the change in time. And we call that velocity. So if my equal sign looks like this, let me take that out. And of course, alright, so now I can draw it nicely here. Very difficult to draw with the mouse. So anyways, here delta S divided by delta T, if I write this in mathematics and formally, your velocity is going to be 0, if your position is the same. Since this is a change, you're going to have a final position, yes, and your initial, So if the final is 10 and your initial is 10, 10 minus 10, the same, So therefore, mathematically, 10 minus 10 is 0, So if your final position and initial position is the same, you will have a 0 for it, okay? Alright, so the velocity is 0 if the position isn't changing and sitting at the same place or same position, because there is no motion. Sitting means I'm not moving, the particle is not moving, the particle is sitting at the same position on that coordinate axis, right? So therefore its velocity, even though the time changes, is going to be 0. So velocity is again dynamics. That's why we call it dynamics. And it depends on whether and how fast, whether and how fast, whether the particle moves, how fast the particle moves. If the particle doesn't move, velocity is 0. If the particle moves, you have to decide whether it's moving, fast or slow, okay? In which direction is this thing moving? You've got to understand that, So anyway, so that is velocity. Alright, then we always have to understand, in dynamics, every, dynamics idea that we've got, we have to understand whether they are vector or scalar, okay? So this thing, velocity, it has a direction, so velocity has the magnitude, how fast, and it has a direction, which way is this particle going. So it's technically a vector, it is a vector. So, but to keep things very simple, we're going to use the signs to indicate the direction of that particle, So the same thing, just like we did before with position, yeah, and the velocity means the particle again. If we put it in a diagram, it's moving in one direction, either this way or that way or some way, yeah. Of course, right now we're just looking on this line, and a positive velocity, okay. Then we have, of course, your negative, yeah, velocity. So positive velocity means the particle is moving in this direction for this example, and a negative velocity means it's going in the opposite direction of that positive direction, okay. So this makes it easier to track the motion without worrying about like arrows for now, yeah. So of course it's not always horizontal diagram like that. Sometimes we draw vertically, yeah. So particle going that way, we call it positive that way, yeah. And so if you go opposite of that positive direction, yeah, you're gonna get the opposite direction, and you can just simply say negative, yeah. It's not only horizontal or vertical, you can go any direction. And if you go that way, just go like that is the positive direction. The complete opposite, meaning like 180-degree apart, okay, is going to be negative, yeah. So if you measure with the angle measurement, yeah, for engineering field, engineering technology field, we have to do a lot of measurement. Your precision accuracy is very important. So from here to here is the direction is 180 degrees, okay, exact. So you will get the opposite directions. All right. Okay. So anyway, that is velocity being a vector. Yeah, it has a magnitude and it has a direction. Then I am going to slowly introduce you the mathematical formula, yeah, for velocity. So we now know velocity is, formally, if we defined it, the rate of change of position with respect to time, yeah. And I should actually write it here with respect to time, okay? So I'm just going to write it T, don't forget that. In fact, I would say like the change of position over the change of time, okay? So that's your velocity C. So the first equation here is for velocity, and we write AVE for average, yeah, average meaning overall, yeah, overall velocity of a particle in the context of our analysis. Yeah, the overall velocity, and we usually write it little v, AVE for average abbreviation, is equal to the change in, okay, position for us divided by the change in time. Don't forget time is changing, okay? Time is not constant, right? Your position is also changing. We're looking at the particle position changing as time goes by, okay? So you have actually two number line, one for time and one for the position, okay? Time is changing. Your particle is also whether it moves, and if it does, how fast, okay, it moves. So that's what we're, let's say like it moves to here, yeah, from here all the way to here. So that's the change here, yeah, change in. And of course, if we look at it, yeah, that change happened about that much of change in time, which is, we call it the change in time. We don't call it change in time, we call it the time interval, yeah, meaning from that point to this point. It's just scientific terms or engineering terms are making you a little bit confused. Just try to get the terms of how we say it, okay? So anyway, so this means we're dividing the total, okay, displacement, don't forget it, the change in position is your displacement by the total time. Yeah, even though we call it the rate of change of position, we formally this delta S is your displacement. Okay, so we can also say displacement, okay, over the change in time, or displacement over time interval. Yeah. So there are many ways of defining velocity. So think of it as the overall, your average is the speed. Of course, this is a velocity, so therefore it has direction, yeah, for that part or trip. The second equation here is instantaneous. Without the average, it isn't overall, it is at a specific time or moment, okay? Specific moment in time is very instantaneous. So the second equation is for instantaneous velocity, okay? Without the average, it isn't overall, and we call that instantaneous, okay, INST, mean instantaneous velocity. So some scholar want to write it INST to remind it is an average, okay? Without it, it's just a plain straight instantaneous velocity is, all right? See this little d. Little t is the same as your displacement, but this means that change is very, very small, okay? So if we go with the derivatives, little d is going to be, the changes very small, very instantaneous. Yeah, that's what we'll talk about here. Of course, we're bringing in some calculus, mathematic terms right here. So that's where it comes from. Little change of position over little change, tiny bitty bit of change of time. Okay, so that's what we're focusing on velocity at a specific moment in time. So the delta S, okay, over delta T is, now I'm going to introduce another mathematic word. It's called the derivative of position, okay? And this is called derivative. So you're going to go DERIVATI, okay, E. So derivative. So this is the derivative of position with respect, of course, to time, okay? Derivative of position over derivative of time, yeah, is equal to, okay, this is just another symbol that is equal to the whole thing. If you don't want to write the whole thing, all you have to do is just S dot. S dot is not purely position, it's just telling you this little dot means do this mathematically, okay? So it tells us the velocity at that exact instant of time. Yeah, sometimes you're going to see with a little dot like that, and don't be confused. So it's just another way to write the same thing using notation for derivatives. No? So if you say like that, it means instantaneous velocity. Okay, that's no position. Instantaneous velocity. My box my box is not containing the dot. Anyways, the dot is in there, yeah. Alright, now we are going to get into the velocity, and you need to visualize how velocity is changing, yeah. So we have our position, and then we have our time graph, and you know that this is position 0, going position some unit here, going position some unit up there, this position is lower than that, yeah, and then come back down and ended up right here. Yeah, so here is your little particle, the green dot. So we're going to connect the velocity, yes, to this graph. Yeah, so velocity, and we can see v1 and v2, and that is the velocity at that moment. Yeah, and you can see, look at that, it's a distinct slope, okay, on that line, on this, in this st. We call this s versus t, position versus time. Your y is always, yeah, before versus, and then your x is after versus. So you mean every time you see v versus y versus x, you know that your y, okay, is your y-axis in the graph. Yeah, so now your y is s, your x is t, y for the vertical, x for the horizontal in your, okay, graph. So I'm gonna write y. So in this case, our y is s, and our x-axis is t, okay, time, and then position, that's where it comes from. Yeah, so your st graph. Okay, so when you look at it, you're gonna, like, see this line. Yeah, see the line and another line here. So these lines, okay, the first line is tangent to that slope. Second line is also, see, tangent to this little curve here. Yeah, at any point on that graph. Yeah, so we draw this. There, the curve is very low curve here. So you can, this is very high curve. So anyway, you tangent it. We say tangent it means draw a line. Yes, cross that particle point on that slope. Okay, so this tangent line slope is going to tell you your instantaneous velocity at that moment. Okay, the moment is t1 here for v1. Instantaneous moment t2 for v2. Yeah, so t1, the slope of the tangent line, going to give you v1. t2, the slope tangent, okay, the tangent slope, this one, is going to give you v2. Okay, what are we doing? We're drawing a diagram, and we are pinpointing to study instantaneous velocity at that time, at that point, at this time, at that point. Okay, this is a particle is taking position. Okay, this is very important, by the way. You must spend time to be able to see the graph. Some students look at the graph but don't really get it. You must spend time. Okay, don't be lazy. This is if you're lazy, you won't be able to see it. Your intelligence is just like machine learning. Okay, your system is just machine. You have to train it. Okay, our machine is not very good. It's because it's made of biochemical material. Yeah, meaning they expand according to whatever you're eating or drinking. Okay, or consuming. Yeah, and putting into your system, it converted to chemicals. Yeah, your chemistry elements, and they combine and try to make the shape as it is defined in your DNA. Okay, so of course it has, okay, it has a particular ratio, okay, in your body. I'm just trying to give you a little bit of knowledge of how your system works. So anyways, you have to train your brain to be able to familiarize with the new knowledge. Okay, so make sure you do that with this example for velocity. Okay, so you can be able to see the instantaneous velocity on a diagram. Okay, so anyway, so let's go back to here. So if your slope, yeah, if your slope is flat, it's going to be 0. Now we have a distant slope, meaning like this slope is going up, that slope is coming down. if your slope is flat like that, okay, drawing on a path of that position line, yeah, it means that you have a zero velocity, okay, because the particle isn't moving. But this guy, when you look at it, it is moving, because see the slope is, see, the slope means this, okay. So if you draw your geometry, yeah, don't forget your mathematics, middle school, I believe, geometry, or maybe elementary, I don't know. So anyway, so this, okay, and that is called slope, yeah, because you have a 90-degree angle right there, and you can be able to see the slope, see it going up slope. This may not coming down, yeah, your slope is going down that way. This is climbing up that way. So if you have a slope, there's a velocity at that, okay, instant time. If your slope is zero, meaning there is no slope at that time, then zero velocity, yeah. This is why we use derivatives for the velocity. It's because we want to, derivative mean we want to see how this little change in, tiny beany bit of change in your position over the change in your time, okay, like that. So when you look at it, there's a distinct change of, position. It went from here to there, yeah, down. And then of course your tiny beany bit of change time from here to there. So we've got that and we've got that. So therefore you have a, okay, instantaneous velocity of that much, okay, which is this guy, yeah, v1, v2. So you v2 minus v1, and that is the your change in position, okay. If you see your s, this is your s1 and then s2, okay, and you're going to get the change in delta s is going to be here, yeah, okay. If you think about the entire path, if you just think about one, okay, point right there, and that would be v1 at that time here, yeah, is a little bit difficult. And at that point it wouldn't be delta s because the path is so small, yeah. So right here you're gonna have this, all right. And right there the same thing with delta s. From here to here you have a bigger, yeah, change. Of course from here to here you also have a bigger change, yes. Okay, all right. I hope you can see instantaneous, yeah. So velocity at a given time, the given time is only one point here, and that is, we can identify that by drawing a line, tangent line, all right, and we call it the slope of that line tangent to that graph, of course. So does everyone see how the slope translates to velocity? Okay, it's very important, very, very important. It's a point velocity. From here to here is a path velocity, because you have a distant change in a position, which is displacement. Here is, you have a displacement, but that displacement is very, very small. It happened at an instant of time, at a moment, and that's why we call this the instantaneous velocity, okay. All right, so the next conceptual example 2.1-2 is for your velocity, yeah. You're gonna do this exercise in class with me, of course at that time, if you do your pre-reading and pre-listening to my lecture right now, you shouldn't have any kind of issue, yeah, because I'm going to explain it for you, because we get only 2 hours, not even 2 hours, yeah. So teachers are getting paid the least, by the way, yeah, but we work, yes, Friday, Saturday, and Sunday, making lectures like that for you guys. Yeah, we have foreign student, we have student from disability, we have student from different backgrounds that they need more time, and this is the reason why we're giving you this lecture. Okay, so you actually lectures about 3-4 hours, yeah, and it's not enough. And some of the administration at school, they don't realize, how much of the times a teacher or professor got to put in, to each class. It's a lot of time right in there. That's why we don't have like time to do any kind of work outside, and we're getting paid the least, but but we have to work very, very long hours to be able to come up with these lectures. So please don't take them for granted, okay? You wouldn't understand right now because you're so young, right? You will understand when you become a professor in later life, if you want to choose this career. A lot of the people do not choose this career because you have to study and spend a lot of time and money to get the degree in order for a person to be qualified for getting the professorship, okay, or job. So anyway, the point is, I spend hours and hours for you guys, okay? So make sure that you do your job, and your job is to study, okay? Study, please. Anyway, so let's go back to the conceptual example 2.1-2. So here in this example, so this is our problem. So it said the following illustration, which is this little guy, show, okay, they show time-lapse pictures, okay, and rolling balls. So these are rolling balls, rolling that way, this way, and that way, with a velocity, okay, in each yes, case. Okay, so there are 4 cases here: A, B, C, and D. So the time between each successive time-lapse image, okay, they equal. So it means we've got a time-based pictures of rolling balls, yeah, and our task is to rank. Yeah, again, we gotta rank it. So we're gonna rank it based on their velocity, okay, from greatest, yeah, to least. So that's what the problem wants you to do. Yeah, do you want me to read this for you? So list each case in order from greatest to least ball velocity. Yeah, here's your ball, and then it has velocity in each case. We have case 1, 2, 3, 4. Yeah, and we name it A, B, C, and D. So you're going to rank it greatest to least ball velocity for the following situations. Yeah, so that's what we're going to do. So let's make it bigger. Yeah, so I'm going to make it bigger so you can see it. Yeah. So when you look at it, A, yes. So A, when you carefully look at it, it shows the velocity, yeah, and the ball. Look at that. So the ball's position, they don't change, yeah, they don't change. You see, like horizontal, yeah. So the ball's position barely changes between images, yeah. So it's almost stationary, okay, meaning like the ball is I would say, I shouldn't say that the ball position doesn't change. The ball position change, but it's changing with the same rate, okay? So it means that from here to here, the change in position, from there to there, your delta S, yeah? And from there to there, and from there to there, from there to there. When you look at it, the delta S's are about the same. So I should say delta S doesn't change. So therefore, the rate is the same, yeah? So the rate of change of delta S is the same. So that's what you're looking at, okay? So therefore, your A shows the least velocity, okay? Why? Because velocity is equal to the change in position over the change in time. Okay? So the change in position is displacement, okay? The displacement divided by change in time. So when you carefully look at the graph, you see that distance is about the same from each position. that this guy is traveling. Yeah, they travel from here to here. So going from here to here, the change is only that much. Going from here to here, the change is about the same. Going from here to here, the Nate's position change the same. Okay, it means that it's going, yeah, time the same thing. Yeah, from here to here, that's your delta t. Yeah, from there to there also delta t, delta t. So all that delta s divided by delta t is about the same. Okay, so another way that you can be able to identify is with the slope. Okay, so if you don't want to calculate, you can eyeball it. Okay, so by looking at this line, tangent line, yeah, so when you look at this tangent line, okay, to the velocity, yeah, you see that it's completely horizontal. It means that your velocity, okay, is the least at that point. Okay, it may be traveling, it may be in motion, but the velocity, okay, you could say is zero. Yeah, zero. Now here, look at this tangent line. See that it's going up like that. So if I draw a triangle, yeah, like that, I should draw. My drawing is not very good, but anyway, so this is your triangle. You see that there's a distinct tangent, okay, with the slope going up, slope, yeah. So therefore, your velocity, yeah, at each point, and if you do consider delta s, you can see, look at that from this distance, yeah, so that's a change. See how delta s varies, okay, so this delta s from time from here to here, another delta s from time from here to here, yeah, that's your delta t, and position change from here to here, so that's your delta s here, yeah, and we do the same thing of course here. So that's the biggest change. A little less, and a little less. So anyway, so from here to here, that's a lot of position change going on for this guy, yeah, which is B. Is you can see the significant movement, though not as much, okay, here. A lot of movement going on, and the slope is, I would say, increasing slope right there, and I would say very steep. Okay, so now when you look at this, a decreasing slope, yeah, because you can be able to draw, yeah, the same thing, your triangle, yeah. So triangle's slope is going that way, so your velocity is decreasing, velocity increasing, velocity doesn't change. Okay, and it is moving, yeah, it is definitely moving. And see, it moves from here to here, and then here to here, and then here to here. So that's all your delta S. I'm not going to draw this like this for you anymore. You understand that as time goes by, the position change, yeah, from here to here. So the ball moves here, yeah, but not as great as that. And when you look at the D, it has significant movement, not like this, even though it looks very horizontal like that, but see, there is a distinct change, even though it is horizontal, yeah. So we can really say that the velocity, okay, doesn't change because it does, yeah. So huge, yeah, huge delta S, we can be able to see that. So I really want you to be able to see the distance. Okay, so if you have a ruler, get a center, yeah. So you have a time interval here, 1, 2, 3, 4, 5 time interval. There's 1, 2, 3, 4 time intervals. You have 1, 2, 3, 4 time intervals. and you have two time intervals here. Yeah, so that's the first thing you have to understand, and the distance, how far away they are. So of course you have all the, you have instantaneous velocities at each point. You also have the average velocity. So when you look at the average velocity, this guy, is about the same. So when you look at the average velocity, this one also is about the same. Yeah. So these are the things that we take a look at it. Okay. So the greatest is B. Yeah, because see like how they change. Okay. We're looking at the starting velocity. So therefore, I'm going to just cut the very first interval is your starting velocity, like that. Okay, so we're getting into the problem. So the problem is go ahead and like rank the starting velocity. So we're going to rank it. This is the least. Okay, so you go, that's the least, because this interval is small. Yeah, because it's the starting velocity. And this, the velocity got to be a little bit faster, greater than A, because of the slope. Okay, so this one is a horizontal slope, so therefore it it is going that way, so it will definitely take greater velocity than A. Okay, because it's tilted down slope. Then we've got this and this. Okay, when you look at it, there's a movement, but the movement is not as great as your B here. Yeah, so you can measure that it has some movement, but the slope is horizontal. Yeah, the slope, this guy is going up this way. Okay, it means that your force is, the source of your force is here at this end, because the motion is going that direction. Okay, so your force is there here, your force is right here. Yeah, so you remember your kinetics. Okay, even though we look at the kinematics here. So this one has more motion, because it went this all the way to here. So more stronger force, it's got to have a bigger velocity. So I'll go B has the greatest velocity, and then D, because this force can push that ball only up to here, which is less interval, and this particle will go, or the ball will go. And that's how we solve this problem. Okay, of course it's set like, it is a starting velocity, and you can also combine if you want. You can combine this and this relatively about the same, and then A and C relatively about the same, because it's not that different. So if you use a ruler and measurement and get accurate distance, they might tie. The same thing with this one. If you think about the intensity of the force is another thing. But it's only say the starting velocity. Without considering anything after that, I would combine it. Okay, so I would rank it like B and D is greater than A and C for the starting velocity. Okay, so that's your answer. Then we're going to do the ending velocity here. Okay, ending velocity, we will be concentrating the end here. So I am going to put my points here. The N is where your arrow is pointing, okay? Don't accidentally define the starting velocity. So ending velocity is at this point. So when you look at it, you can see, yeah, this two, yeah, look at that. They're smaller than this, yeah, distance. So this is your delta S. So that's your delta S. This is your delta S, and then that's your delta S, okay? And the ball moves, yeah? So A, but not as close as that, yeah? So B has the least ending velocity because this movement is small, yeah? This one movement is, there's a bigger gap than that. So your delta S is bigger than this, therefore your velocity is bigger. So we're gonna rank A velocity is bigger than B velocity. Then C and D, when you look at it, okay, D, you're gonna measure from here to here, so delta S, from here to here, it's about the same to me, yeah? So we're gonna just tie it. So that's greater. Why? Because the delta S is bigger than this too, so therefore your velocity is bigger, yeah? Because velocity is the delta S divided by your delta T. Yeah. All right, so that's how we solve this problem for conceptual example 2.1. And this is asking you to find a constant velocity, yeah, situation. So we have 4 situations here, and cases, actually 4 cases here. The constant velocity is when your delta S, all right, doesn't change. So delta S divided by delta T is your velocity. See this? Yeah, and your delta S here. So look at this. That's the same, yeah, and of course your slope is 0 here. So therefore it doesn't really change, okay? Don't forget the slope at a point, okay? If that is here, yeah, and if we're just concentrating at that point, and then your instantaneous velocity would be 0, yeah? But for a series of events like that, even though we're on the horizontal path, yeah, you have a distinct intervals, and in there your delta S, okay, each one of the interval really doesn't change, so therefore it's going with a constant velocity. Now you have 3 different velocity. One is a constant, second one is the average, and the third one is your instantaneous velocity, right? So make sure you get the 3. Yes, you have to know the differences between the 3 types of velocities, okay? Because so the answer is this and that, yeah? Because it's really constant, going from here to here and from here to here is the same velocity. So A is, yeah, showing the constant velocity, because for velocity to be constant, the spacing, yeah, between the position in this diagram needs to stay the same throughout the motion. Your motion is from here to here, yeah? And of course, here the same thing, yeah? The velocity is constant because the spacing from here to here between the positions, right, in this diagram is yeah, it stay the same throughout the motion, yeah? So it means that the ball isn't speeding up or slowing down, okay? It is moving steadily with constant velocity, okay? On the other hand, if you look at the B and C, look at that, yeah? See that space? Yeah, it's changing. Yeah, so it has changing space. Look at that, the spacing here, spacing there, the gap here. Yeah, they're changing. They're not constant like that. Yeah, the change isn't constant in C and B. The change of the spacing here is the same. So B and C, their velocity ain't constant. Yeah, they're speeding up or slowing down. In fact, I suppose to say this is speeding up and that is slowing down. Yeah, in two different ways you can be able to read it. If you think like the force is going, even though it is going down slope with this vector direction, yeah, it might have more speed than that because it's going uphill here. Yeah, even though your forces push them up and your motion go that way direction, your speed is actually slowing down here. Yeah, be careful of these little things. So I hope, does this idea of constant spacing is your constant velocity, does it make sense to you? You have to ask yourself. If you have a question, ask me, in class. Alright, so the next question is your conceptual example 2.1-3. So when you look at it, we got to rank again, rank them based on the greatest again to least, but this time we're gonna concentrate on the instantaneous velocity, and of course the same time interval 0 to 3 seconds. All right, so still have our ST graph, your time, your position here. You know how to read the position 20 units 10. I'm gonna go a little faster. 20 to 0, and then 0 back to 20, 10 to 20, and then here going down and then come back down. Okay, so now we know how to pinpoint the position change. Okay, so again, don't forget we're now in instantaneous velocity, so you have a tiny little bit of change in position, okay, divided by a tiny little bit of change in your time. It's only 3-second change. So this is d delta, delta s. I should write it this way better. Delta s divided by delta t. Okay, so that's your instantaneous velocity. That handwriting is very bad. My handwriting is very bad. Oh, don't be like me. So anyway, so yeah, my handwriting is chaotic, but my brain, inside of my brain, is very clear. Okay, so in order for us to find the instantaneous velocity, now we are going to use our slope method. So the steeper the slope, the greater the velocity at that moment. The steeper the slope, the greater the velocity at that moment. So when you take a look at it, F has the steepest slope at its peak. Okay, so when you look at it, that's the steepest slope ever. Steeper than this and this and that slope. So it's going to have the greatest instantaneous velocity at that point. Instantaneous velocity, okay? From 0 to 3, bang. All right, the next one, when you look at the slope, we're going to see D, okay? And it's a positive slope. And C has a negative slope, but that and this, okay, if you think about the magnitude of the velocity, about the same. So I will go, F is the greatest, followed by C and D, Then we have the next one, which is your E, And the last one is your flat line, that is your A and B, So your A and B have like the least slope, no slope at all. Actually, this means 0, velocity at that point. now we come into, we're gonna rank them again, greatest to least, average. Yeah, so we have AVE. Anyway, so this AVE, hard to write. So anyways, average velocity, you're gonna be having delta S, yes, and delta T. But now we're looking at a bigger interval, yeah? Remember your average velocity, it means that we're gonna compare the total, yeah, the total change in position over that 0 to 3 second instead of the instantaneous point. So we have total time interval is 3 seconds, and we're gonna look at it. Okay, I need you to see a little bit bigger, yeah, diagram. So we have C and D, yeah, the greatest, is because when you look at this C and D, say that it has a positive slope from 0 all the way to 3, okay? And we're looking at the average, yeah, velocity. So the change is from 0 to 20, so that's a 20, yeah, divided by 3. Then this guy, yeah, 20 divided by 3 time interval, so which is 3 seconds. Then we've got E, which is your 10 divided by your 3 seconds. Okay. Then we have A and B and F is the same thing, but that's 0, 0, and 0. Okay, because we're looking at the change. Yeah, so don't forget the change. Don't forget the equation. Yep, I am very fast. It's because in my head there is delta S. Yeah, make sure that in your head you know that this number is this. Okay, delta S, which is final minus initial. Yeah, I'm just gonna write F minus I for initial. Yeah, so that's what we're doing. 0 minus 0. Yeah, 0. This is 0 because it changes 20 minus 20, 10 minus 10. The change is, yeah, 20 minus 0. This is 0 minus 20, and then 10 minus 20 is minus 10. Yeah, minus and plus are direction, they're not value, so therefore you don't have to worry about that. So anyway, so put this in and you get these value and you compare it. So we're gonna rank it. This is the highest, greatest, second greatest, and zeros are your least, yeah, average velocity. All right, the next conceptual example problem. So we have a car, and that car drives along this straight road, and then the car's position changes with time. Okay, so here is your position. It's going to change with time, and we put it in a ST graph. This one is S as a function of time. Okay, this is not pure S, it's showing you ST, yeah? So that's mean the car's position changes, and then with time it's shown in this graph. So you have ST versus, because ST is your y-axis, and then T is your x-axis, yeah? ST versus T, ST versus T. So now we have MCQ. I call it MCQ. Q for question, M for multiple, C for choice. So when we say MCQ, it means multiple choice question, which is A, B, C, D, 4 situations given to you. You're going to choose the best one. Yeah, doesn't have to be accurate, but the best situation is your correct answer. So the graph indicates that this graph, what is this? Yeah, so we know that this is a ST versus T graph. So we're seeing ST position as a function of time, yeah, against time. So the car speeds up with time. The car slows down with time. The car initially speeds up and then slows down. So the car moves with a constant velocity. Okay, we gotta choose what's going on with that thing. Alright, so the answer is the car slows down with time. Okay, for me it's very easy to look at it because we can identify that. For you, you're gonna have an issue if you don't understand what this is about. Okay, so you gotta understand what ST means, because ST is not S. It's definitely not position. Okay, because you have a time factor in the bracket. Okay, this is the first thing you have to understand what you're looking at. Okay, so ST is, it represents your position, yeah, of that particle, but as a function of time. Yeah, so mathematics is already in there. So we're looking at position, but you have to function with your time. Yeah, so as a function of time. So it means in a simple way, it tells you where your object is located at any given time. Yeah, at this time, where is it? At that time, where is that? So that is what you're seeing against another time factor. Okay, so yes, so this is over time, and this is at a time. Okay, so S is a position, yes, on the coordinate axis, and then your T is the time. Okay, and we're putting that onto this over time. And so when you look at ST, we can understand how the position changes over time. Yeah, so your ST is a straight line with a constant slope. If your ST is a straight line, yeah, with a constant slope, okay, so you will have to draw, like a tangent line like that. Okay, I can draw first tangent line, I can draw another tangent line like that, and then you have another tangent line like this. Okay, so anyway, so my drawing is not very good. I was supposed to make it real line. Okay, let me see if I have a line or something. Oh, here I have a line here. So yeah, it's so hard to draw a line here. Oh my gosh. One moment. So yes, I successfully drew a tangent line. So anyway, you can see this line, see? So you have to draw this slope lines, yeah, on the path in order for you to be able to understand that ST, okay, meaning. So every time you draw like that, a perfect, yeah, tangent line, and if that straight line is a constant slope, yeah, so from here to here, your object or your particle, yeah, is moving at a constant velocity. So you have a constant velocity here, and the slope is going up. Yeah, it means a steep slope, meaning it is speeding up. Yeah, so then you can draw another line here. See, yeah, so see how the curve going. So you're gonna have a different tangent line going. Okay, let me draw again. Okay, now I drew another tangent line right there. See how this slope and that slope is totally different? Meaning like this slope is steeper than that, yeah? So the steeper the slope, your velocity, okay, is actually, this is more speeding up than that point from here to here, okay? Because all these points on this line, okay, from this to this has that slope. From here, okay, from here to here has that slope. So this is the particle is speeding up, but this speed is higher than that speed because of the slope is shallower, yeah, for these points. And then of course you can draw another, okay, another tangent line at the end. So now I drew the third, all right, tangent line at the end, yeah. So beginning, speeding up. There is speed, but this speed is less than the initial speed. And now at the end, look at that slope, yeah. It's almost flat. My line is not very good in drawing, but it's when you actually look, it's really speed is almost zero at the end. Okay, so it means that the car slows down with time. Okay, so this time is actually that, yeah. So this is, we're looking at the velocity, okay, the velocity of a particle over time, yeah. So simply put, every time you see st, you know that you're dealing with a position, okay, as a function of time, which is velocity. Okay, it's just a writing is another mathematics or symbols or way of writing as t, as in a bracket t, okay, not as this, all right, is not the same, okay, it isn't the same as this, all right. This means position times t, this means position as a function of time, which is velocity, okay. You're looking at velocity over time. All right, so speeding up, speed slows, your speed is slowing down, and then your speed is even slowing, okay, than it was before, okay. So the car is slowing down with time. Don't confuse that time and this time. This time is already calculated, okay, because we're looking at the velocity graph over time, okay. So this is a velocity graph over time. So now you have we have st graph, and you have velocity graph, which is position as a function of time, all right, dash t time, st t time, okay, t, which is time graph, right? st graph and stt graph, two different things, and we call this vt graph, right? Even though we write this way, in our brain we read this way. Okay, all right. Slope, steep, speeding up. Slope, shallow. Speeding is there, but not as much as with the steeper slope. Slope is very shallow, almost horizontal, and then your speed is going towards zero, yeah. So meaning the car slows down over time. All right, so what I'm going to do is I'm going to stop here as a part number 2 for this lecture, and we're going to get into another section, okay.